Time is 2:30, so let's begin here. So day number 1 quiz is due now. If for some reason you were unable to complete it, please come talk to me after class. Some other announcements. First of all, regarding the book, for those of you who have not received it yet, did it by chance arrive from the boat, from the dock?
I ordered it from Amazon instead. I'm just going to return the one when it shows up.
That might actually be the best bet. I contacted the editor for my book, and this is what he told me, that it's out of stock in the U.S., at least from CRC itself, which I think is now obvious, and it's overstock in the U.K. And I was surprised when he told me this. It has sold 550 copies already, and this is out of 750 that were printed in the first printing, and so they're doing another printing of it, but obviously it's going to take time to do that. And in the meantime, they're sending some of their stock from the UK over here, but you know, if it's coming by boat, it's going to take a while. He said that that in their distribution center, they're expecting the book to arrive in February. Give you some ideas. So, what I recommend that you do, as we just said a minute ago, you might want to look for alternatives. I did just go over to the East Campus Union Bookstore, and there's one copy there. At least at the Nebraska bookstore itself, it says it is in store, so that's a good sign. And the University Bookstore itself, which I guess includes the East Campus Bookstore. I don't know if they're also talking about the City Campus Bookstore, but here for in stock, it says, well, maybe purchased from the local store or another location. Well, that scares me a little bit, so I don't want to have to wait any time. So I don't know about the City Campus, if they have copies down there, but they at least do have one copy here at the East Campus Union. So I apologize for trying to save you some money and telling some of you or suggesting to buy it from CRC Press. It was meant to make your life easier. Instead, it made your life more difficult. And I'm sorry that I did that. Any questions regarding the book?
Yeah. I ordered one from Amazon on Tuesday.
Okay.
It's being shipped from New Jersey.
Really?
Yeah.
Okay. Hopefully it won't take too long. Hopefully you're an Amazon Prime member and you can get it in. You should write today. Oh. I love Amazon Prime. My wife decided to do it a few years ago. I said, I don't want to spend the 80 or whatever bucks for it. But now I'm hooked on it, to be honest. 2-day delivery, can't beat that.
You said that chapter 1 was online?
Chapter 1 is online, so it's not necessarily, a huge concern because chapter 1's online and you can see.
How do we get access?
If you go to the book's website itself, chrisboer.com/categorical, you'll see a link to the Google Books. So it's like a Google Books preview, essentially. The only thing that you're missing then in the meantime is Appendix A, which is very, very close to my Introduction to R notes, the paper copies, and also Appendix B. And there's some stuff that I will reference actually today from it, but you can probably get by without it. And they're appendices. So that's what happens with a lot of appendices. Okay, so also with respect to the Introduction to R, I just want to bring your attention to this. I know this isn't shown the best here, but there is a Introduction to R workshop that's being held Wednesday, January 21st and Thursday, January 22nd. Unfortunately, the Thursday version overlaps with our class, so that's not an excuse to skip class. But maybe at least the first day might be helpful. To be honest, I think you'll get enough out of the Introduction to R video and notes that I gave you, and also obviously I will be going kind of slow through the R stuff at least at first. So personally, I don't think you need it, but if you do feel as though that you want some more, this is an opportunity. It's nice to see something like this available for students. I'd never seen something like that before. In fact, I was asked actually to give an introduction to R workshop last year, and I said, sure, I'll do it. But unfortunately, the people who were organizing it never continued to organize it. And it didn't happen. So were there any questions regarding the R introduction, the notes and the corresponding video? Any questions? Okay, silence means no. You completely understood it, and you did watch all parts of it. So we will continue here then today. Are there any questions overall before we get going? Okay, good. We left off in the notes on approximately page 1.8. So last time, a lot of the statistical content, not necessarily the R stuff, but the statistical content was largely should be reviewed. You know, your first stat course, you do talk about a binomial distribution. I've never known a first stat course that didn't ever do that. So we looked at some examples, how to calculate some probabilities associated with the binomial. Now we're going to talk about another example where we're looking at simulating observations from a binomial distribution. In other words, I want to use the computer to simulate what could happen if I, let's say, went out and kicked 5 field goals. How many successes would I have had? Suppose I go out and kick another 5 field goals. How many successes would I have? Well, we can have the computer simulate that for us. Now, before we get into, well, how you would do that, why do you think maybe we would want a computer to be able to simulate it for us? What do you think?
To evaluate whether the probabilities are actually what?
I think you're getting at it, and that is, you know, all the stuff that we have,
Ordinary and the variance of the.
yeah, and check the variance too.
Yeah.
Yeah, and, you know, we have a lot of underlying assumptions, you know, for like confidence interval procedures, for hypothesis test procedures. You know, one of the assumptions then for maybe a test statistic that we will have is that we have an underlying binomial distribution. And in order to check to see if an inference procedure like confidence intervals or hypothesis test works, one way to do that is to have the ability to simulate some data that satisfies the assumptions and try out that inference procedure, like a confidence interval, on it and see, did it work? Is it working as we would expect? That's why we want to have the ability to be able to simulate this stuff. So we're going to talk about how to do that. No. Okay. So to simulate observations from a binomial distribution R, there's a function called R binom. You know, there's something similar in Excel as well, and it works in a very similar way, except for you don't have like cells in a spreadsheet. And so the R binom function stands for random binomial, does the simulation for us. So what I'm going to do is come over here to 10. In the introduction to R video, you saw me use 10 to do some of this stuff, or to look at my R program. I typically use 10 rather than RStudio. Please feel free to use RStudio. I think the majority, I wouldn't say most, the majority of students do use RStudio. There's some aspects of 10 that I think are better, so that's why I use it. And so what I have here is my program. It's my binomial.R program that you can download from my book's website. And, oops, sorry, I'm on the wrong program. There it is. Okay, so there's my binomial.R program. And we looked at some of the code associated with it in our last class, even though we weren't looking at it in 10. And what I want to come down here is to where I actually start simulating observations from a binomial distribution. So the way that we can do that is use our binom function. The first argument corresponds to, well, how many observations do I want? How about 1,000? Just so we get a large number to see what happens. And so the first argument, n, corresponds to number of observations, not number of trials, as in our notation, number of observations. Size, again, corresponds to Rn in the notes, the number of trials, 5. So for each of these 1,000 observations, there's going to be 5 trials per time. And our pi is denoted by prob, and it's going to be 0.6. I'm going to put the results in an object called bin5. And everything went in there. Now, if I want to see what's inside bin5, what would I do? Just type it and hit enter. Well, there's 1,000 things in there. I don't want to see it all. So what I'm going to do instead is look at, let's say, just the first 10. And the way I can do that is put 1:10 in there. Remember what that's going to be. 1, 2, 3, all the way up to 10. And what that's going to tell R, pick these first 10 items out of the vector that is bin5 and show them to me. Okay? So, first time, 2 out of 5 successes. Second time, 2 out of 5 successes. Third time, 4 out of 5. Now, let's run this code again. Now, I don't remember if I showed this in my video. One quick way to cycle through maybe past code that you've run in the past is to use the up arrow. So I'm going to hit the up arrow twice, and I go back 2 lines of code. And I'm going to run it again. And this is what I get. So I got different data. Why is that? Well, I'm simulating data. And so you shouldn't expect exactly the same thing every single time. How could I make sure I get the same results? You know, like let's say for the reproducibility of whatever calculation I'm making. I can do what's called set a seed. Now, hopefully in your first stat course you talked about random number generation, but still I think sometimes that's not talked about. At least I always talk about when I teach a course like Stat 801. I spend a lot of time talking about it. To set a seed, you can think of it this way. You know, think of it like a regular old seed, something that you plant in the ground, and you know, some plant would sprout out and come out. So you know, everything's starting essentially from that seed. And in a computer science sense, when you're simulating observations like this in a random manner, what that seed does is it basically gives, in this case, our binomial a starting place. And so that if you always use this starting place every single time, you'll always get exactly the same results back when you simulate the data. Now, to set a seed in R, I'm going to use a function called set.seed. And my seed number, I just chose it. I could have chose any number I wanted to. I just, let's say, in the random number generator in my head, I chose 4848 for some reason. Okay, so I'm going to set my seed. And then let's run the same kind of code. And I get those observations. Let's do this again. So I'm going to come up here to my, go away. I'm going to come up here. Let's hope that doesn't happen again. I'm going to come up here to, jeez. Now you're probably saying, why don't you just use RStudio? No, 10 is better. Let's close it out and come back in. This is the only problem I've had with 10 is sometimes you'll have that happen. And I have not been able to figure out the reasoning. I thought about contacting the author of it, and I just haven't got to it, but he does proudly display on his website that I use it. And so, okay, so I simulated the data. Let's do it one more time. And I get exactly the same results. Okay, took longer than it should have. I don't think it's really of interest to us to know how that 4848 is actually used inside of our binomial. Just to understand that whenever I set the seed, and I do it, let's say, right before the function I run, I will get the same results back. Okay. Any questions about that? Okay. So now, what do you think then the mean, without looking at the notes, what do you think then the mean of all these 1,000 observations should be about?
3.
About 3. Why? N times pi. Remember that was the expected value of W, the number of successes. N is 5, pi is 0.6. So we should get what we expect. And in fact, we do. And if I did var, and I should say, I use the mean function. It makes sense. You know, in Excel you have the average function. Well, this is, we're statistics. Well, this is made by statisticians, so that's why we use the word mean. There's also a function called var for variance. So if I want to find the sample variance of all these 1,000 numbers, oops, I could do that with the var function. I get 1.23. So if I take, check that, take 5 times 0.6 times 1 minus 0.6. Remember that was the formula for a variance, the variance of W. Oops, what did I do wrong? There we go. And we see we get just about the same results. So this is good. You know, what this is kind of saying is that, well, how you simulated it was correct. Okay. Now we will come back to, I guess I'm sorry, I'm getting ahead of myself. Well, how about we actually look at, well, how frequent we got, let's say, a 0, how frequent we got a 1, how frequent we got a 5. We can do that using a function called table. If I say table, the default argument is x. I say table x equal bin 5, or I could just say table bin 5 itself. This is what I get. Now remember, there's 1,000 of these numbers, so that means the proportion of times that I got 3 was 36.2%, or 0.362. Well, how about we go back to our actual probability distribution that we saw last time. We saw the probability that W is equal to 3 was about 0.35. So again, we're getting what we expect. And you can even do a little histogram of all the data as well. There's a function called hist to do histograms. The first argument, x, is your data that you're plotting, bin 5. I'm going to put a nice little title on my plot. I'm going to tell R that I want the y-axis of the plot not to be counts as you would normally have in a histogram. Instead, how about we do relative frequencies for proportions? And it just so happens the argument happens to be called probability. Probability equal true. The default is false. And then I put a y-axis label there. And this is what I get. Here's my histogram. So if you notice that what will be W equal 3, if you come up here, oops, did I do that right? I apologize. Okay. Let's try this instead. Not sure what I did there. That looks better. So at W equal 3, you can see the height of the bar is about 0.36, is what we just saw when we ran the table function. If you see where my mouse is, right over there. So it's just a graphical picture of it. Now note that it just so happens with this particular data, the histogram looks better if you actually specify what are called the breaks in a histogram. In other words, the boundaries for the classes. So if you remember when you've done like a histogram in your first stat course, you have to specify, okay, I want to find all observations, let's say between negative 0.5 and positive 0.5. All observations between 0.5 and 1.5. And that's essentially what I'm doing there. Most often you don't have to do it, and R gets the plot to look right, but if you take it out, for some reason it doesn't look very well this particular time. Okay. So we will be doing some more simulation later. It's just now was a good time to introduce the idea of simulation right after we first introduced the binomial distribution. Are there any questions? Okay. So page 11 then. Our goal now is to be able to come up with a confidence interval for pi. Now, I would imagine, again, in your first stat course, you've probably talked about a particular confidence interval for pi. It might look something like this. Let's say your sample proportion plus or minus a value from your standard normal distribution. Let's say your 1 minus alpha divided by 2 quantile, like if alpha was 0.05, this would be 1.96. And then you take it times the square root of your proportion, sample proportion, times 1 minus that proportion, divided by your sample size. Does this look familiar? Just a second. I was looking down when I asked that question. I didn't hear anyone say anything. Does this look familiar at all?
Mm-hmm.
Yeah, okay. Don't ever use that confidence interval. It's a bad one. Okay? Which is odd for me to say that because, in your first stat course, in fact, before I knew this, I always taught this interval. You'll understand what I mean by bad shortly. And I will present alternatives. Okay? So to begin with, though, we need to figure out, well, how would we estimate pi? And one of the most general estimation procedures out there is called maximum likelihood estimation. I wouldn't be surprised if at least half of you have used maximum likelihood estimation before. Maybe you've used it in a context where you didn't really know what it was doing, just that, hey, I got a number out, it was my estimate. But I still also wouldn't be surprised if there were some of you who never used it. And there's probably some of you who understand the mathematics behind how maximum likelihood estimation works. We're going to do a short introduction to maximum likelihood estimation. We will use maximum likelihood estimation for the rest of this course. Okay? Now note that some of this material is taken from Appendix B. So again, if you feel as though that might help you, I think you'll be fine with this, but if you feel as though that might help you, let me know and I can see what I can do. So let's put this into a context of an example to help you understand it. Again, let's look at, we are interested in modeling the success or failure of a field goal. And what we want to know is, well, what would be a good estimate for pi, the probability of success? So let's let y equal 1 be a 1 if the field goal is good or a success, y equal 0 for a failure. And here's the old Bernoulli distribution that we saw before. For that, we're going to use that as our probability distribution to model this. So let's say that we want to estimate pi for a 40-yard field goal, and we keep constant all the other factors like wind and stuff like that. And we go out and we observe n different field goals that are being attempted. Let's assume that they're all independent. Let's not worry about dependence. So maybe n was 10. And so what we get back then is a bunch of, if we think of it in a mathematical sense, what we get back is a bunch of zeros and ones. Zeros for failures, ones for successes. And using that information, given this information that we have observed in our sample, we can form what's called a likelihood function. And what this likelihood function does, it measures the plausibility of possible values of pi. For example, how plausible is having pi be equal to 0.2 if I observe 4 out of 10 successes? If I observe 4 successes out of 10 trials. How plausible is pi equal 0.4? How plausible is pi equal 0.99 if I observe a certain number of successes out of a particular number of trials? So the likelihood function gives us a mathematical way to examine that. And this is what it looks like. So I use L to denote likelihood. It's a function of pi. That's the thing that's going to vary in it, or I shouldn't say vary in it, but is unknown in it. And in your other stat courses, when you've drawn like a vertical line like that, what would you say? How would you verbalize that?
Given.
Conditional or given. So the likelihood function of pi given, I've observed a particular value of y1, particular value of y2, and so on. And all it is just simply the product of, well, whatever y1 was. I'm sorry, the product, let me see that. All it is the probability y1 is equal to whatever you observe, times the probability what y2 is, times the probability of what y3 is, in terms of what it was observed. And I can simplify that, put it in a little bit more succinct manner by using some product notation. In case you've never seen that before, it works just like a summation symbol, except now you're multiplying stuff together. And so now, let me check my battery here. I just want to make sure. Good. So now, how about I put in the Bernoulli distribution that we saw. But I make one little addition here. Notice I have a subscript I there to represent which observation. Was it the first time I kicked the field goal? Was it the second time? And so on. Then I can do some nice simplifications. Because of course, if I have say, pi y1, 1 minus pi, 1 minus y1, times pi y2, times 1 minus pi, 1 minus y2, and I keep on going. Notice that what these guys have in common. So in other words, this part right here would be pi raised to the y1 plus y2 plus all the way down to yn. So that's why I have a summation here. We do the same thing with the 1 minus pi's as well. And as a little bit of a shortcut, we can say W is equal to the number of successes. So the sum of the y's. So I have pi raised to the W times 1 minus pi raised to the n minus W. Let's say then I did observe 4 successes out of 10 trials. Let's look at the likelihood function. Let's evaluate it for different possible values of pi to check which value of pi is the most plausible. The value of pi that maximizes this function is the one that's most plausible. And so let's look. So at pi equal to 0.2, I get 0.000419. When I increase pi to 0.3, my likelihood function increases, so that's good. And if you look through all those numbers there, you can see where you reach the maximum value is at pi equal 0.4. So the most plausible value of pi is 0.4. This is called then a maximum likelihood estimate. Obviously, in this case, it's intuitive. 4 successes out of 10 trials, so 40% of the time you're making it. Okay, yeah, that makes sense. Why don't we use that as my estimate for what I think overall what my pi would be if I were to, let's say, do this an infinite number of times. Here's a little graph. Yeah?
Those likelihoods, so we will never do this by hand, but if we were to use maximum likelihood in R, does it actually calculate the likelihood for all the possible values of pi?
Well, there are more mathematical ways to do it. I'm trying to give it some intuitive explanation of how this comes about. And what you're going to see shortly, we can actually use some calculus to get a closed form solution. But again, we'll be using maximum likelihood estimation throughout the semester, and there's going to be many cases where we don't have a closed form solution. And there are numerical iterative methods that are used to search for the value of whatever our parameter is that maximizes our likelihood function. Will I ask you on a test ever to write out all possible values of pi, tell me what the likelihood function is? No. This is more just right now an introduction to what likelihood estimation is, so that when we get to more complicated examples, you'll say, okay, yeah, I understand how you're doing, what you're doing, and we're going to have R, do the hard calculations for us. Okay. Here's a plot of the likelihood function, and if I come down here, here's 0.4. If I come up, you can see that indeed, I can't draw very well, But it looks like at pi equal 0.4, that's where the maximum occurs. Okay. Just a little side note, how did I do this plot? First of all, make sure on your own you understand these calculations here. These are very similar to the ones that I did during the first class. To do this plot here, I use I think what is a really cool function called curve, which allows you simply to draw, some function of x. Okay? So let's say, for example, I want to draw my plot. I want to draw a plot that has y equal x squared. Okay? So I can go over here to R, and I'm going to use the curve function. The first argument is called expr, which stands for expression. And this is where you put, well, in terms of x, what you want. This has to have an x there. Okay, so I can't have like a w, I can't have an a. Whatever you want on the x-axis has to be shown there. It has to be written in terms of x. And then let's say that I want to draw this plot for a limited part of my x-axis. Let's say from -1 to +2. So I can do x-lim for x-axis limits. I'm going to combine -1 and 2 into a vector. The first number is going to be the minimum on the x-axis. The last number is going to be the maximum. And then up, what should have occurred is here's my plot of y equal x squared. So now extending this to our particular case, what I want to do is actually draw then the likelihood function itself. Where is it? So what I'm going to do is for expr, I'm going to put in x raised to essentially my w power times 1 minus x raised to my n minus w power. Sum dot y has been set to, that's my w, has been set to 4. Set my x-axis limits. This x label here, what I could have just done was something like this, parentheses, pi, and parentheses, and you have how you would verbalize the Greek symbol pi. If you want to know how you can actually get Greek symbols on plots, there's a nice function called expression, and you put in parentheses, well, pi, or let's say if you wanted alpha for some reason, well, type out alpha, the word alpha. I put a y-axis label on it, and that's how I got my plot. So again, make sure you can run the code. The program is, the corresponding program, which is shown right here, is available on my book's website. Okay, so pi equal 0.4 is our maximum likelihood estimator. I'm sorry, 0.4 is our maximum likelihood estimate. Now there's actually a general way that you can find maximum likelihood estimators. Let's just go through this real quick. Calculus is not a required for this class. I think it should be, but that's just the way it is. It's not. So I will at times show a little bit of calculus, but whenever you do see calculus, I will not, let's say, require you to do it on like a test. Okay? So this is just, since I think probably most of you do have calculus, that's the purpose of this. Okay, so in like a Calc 2 class, if you take the full 3 semesters of calculus, you learn how to find a value that maximizes or minimizes a function. And essentially that's what I'm going to do here. Instead of just working with the likelihood function itself, I'm going to work with the log likelihood function. And that, the maximum of the likelihood function, the pi that maximizes the likelihood function, is also going to be exactly the same for the log likelihood function. The reason, if you want to think of it in a mathematical sense, is that the log function is a monotone transformation. Just trust me, it is the maximum occurs at the same spot. So I'm going to work with the log likelihood function, and what this is going to do is simplify some of my math coming up. I'm going to then take the derivative of the log likelihood function with respect to pi. I'm going to set the derivative equal to 0, and then solve for pi. As long as some assumptions are satisfied with this particular kind of function, the value of pi that maximizes this function will be then the solution when I set then this first derivative equal to 0 and solve for pi. So let's try this. So with the field goal kicking example, here is my log likelihood function. And so log, and then this is exactly what I had before. Now this is why I take the log. Notice if I had, let's say, the log of a raised to the b power, that's b times log a. Well, I got that thing going on here. I got that kind of thing going on there as well. Also, if I had, let's say, log, this is natural log, by the way, log a times b, what's that? Yeah, log a plus log b. So essentially, if I draw a line here, I got that kind of thing going on as well. So then this has how my log likelihood function simplifies down to that portion there. I take first derivative with respect to pi. This is what I get. Set equal to 0, do some algebra, and what do you know? This is my maximum likelihood estimator. The sum of the y's divided by n. In other words, number of successes divided by number of trials. Again, intuitive. This is what we had when we looked at all possible values of pi essentially, and we saw, okay, 0.4 was what maximized that likelihood function when we had 4 successes out of 10 trials. Now, pi is actually a parameter itself. And to not confuse the parameter with the statistic that's trying to estimate it, rather than calling this equal to pi, we will put a little hat on top of pi and call that the maximum likelihood estimator. Please make sure you always do that. I will always take off points if you don't do that. It just gets back to your first stat course. There's a difference between a statistic and a parameter. We need to denote them differently. Okay? One's going to have a hat, one's not. Okay. If you want to know a little bit more about the mathematics behind maximum likelihood estimation, you can take a look at my Stat 380 course lecture notes. This is an intro stat course, often the first stat course that undergraduates have, but these undergraduates have calculus as have had calculus before. Okay, so there are some nice properties of working with maximum likelihood estimators. Some really, really nice properties. Now we know that this is an estimator. This pi hat's an estimator. So if I go out and kick 10 field goals now and get the estimate, do you think I will get exactly the same thing if I go out to kick 10 field goals tomorrow? Probably not. It's going to vary from sample to sample to sample. And in statistics, what we're really interested in is how can I quantify this variation? Because if I can quantify it, then I know, what's going on. I know what should happen in the future, generally speaking. So, with this maximum likelihood estimator, then we have these nice properties that make them very useful. First of all, again, think of pi hat as a random variable. It's going to vary from sample to sample to sample. For a large sample, continue to repeat this sampling process over and over again, you'll see this pi hat essentially has a normal distribution to it. That's how it varies. The same way as a regular old normal distribution. Make sure to put it into context. Suppose I repeated this field goal kicking experiment 100 times. And every single time I calculated pi hat. If you did a histogram of all those pi hats, what do you think the histogram would look like? What's your shape? Symmetric, kind of bell curve-ish. Okay? That's what I'm talking about. Second property, which was left out of your notes. So whenever always before class, I go through my notes. In fact, I usually just say the lecture in my head to make sure everything's going to work out fine. And when I do that, I might think, uh-oh, I forgot something. And so if I forget something, I will denote it with blue text up there. I will generally remember to tell you that in class, but if I don't, look for the blue text. Okay, so now for a large sample then, the expected value of this maximum likelihood estimator is approximately equal to the parameters estimated. Well, that's good. So what that's saying is for a large sample, what I would expect pi hat to be is approximately equal to pi. That's a good property to have. Very good property to have. If you've ever heard of unbiased estimators before, this isn't exactly, I'm not necessarily calling this an unbiased estimator, but for large samples, this essentially is. Okay? Good property to have. Also for a large sample, I can calculate the variance. So I know how that pi hat will vary from sample to sample to sample, in addition to knowing the entire probability distribution itself. And this variance, unfortunately, is not necessarily, as you'll see in the formula itself, it's not necessarily something that looks pretty. It's actually based upon the second derivative of the log likelihood function. So if we put these three properties together, this is what it looks like in a mathematical sense. If I have just a general overall maximum likelihood estimator, let's call it theta hat, that's trying to estimate theta. Theta hat, this little tilde here, if you've never seen this before, means distributed as. When I put a little dot on top of it, it means approximately distributed as. Okay, often in your first stat course, you'll see something like this. X is distributed normal with a mean mu, variance sigma squared. That's where this is covered. But some people just will not necessarily use that tilde, so that's why I wanted to bring that up. So theta hat is approximately distributed as a normal random variable with a mean of theta, comes from property number 2, and a particular variance. Notice how I have a hat on top of there? That means that this is an estimated variance. This works for a large sample. Don't worry about what I mean by large sample right now. Just realize it's large enough. Okay? Don't ever ask a statistician how large of a sample should you have, because they won't tell you. They won't say n should be equal to such and such. They'll just say, well, it needs to be large. This is what this variance looks like. So you can see it's a little bit messy, but it's really not too bad. I'll never ask you to calculate one of these things, let's say by hand, actually writing it out, taking the derivatives and stuff like that. But you need to know the basics of what it is, and we will have R, do the calculation for us in an automatic sense. So let's briefly talk about this. So first of all, this is a negative sign. So inside here, you see the log likelihood function. Log likelihood function for theta, given my data y1 through yn. I'm taking the second derivative with respect to theta, and then I take the expected value with respect to the distribution for y. I invert all this, and then wherever you see a theta in the end, put a theta hat. Because this needs to be something we can actually numerically calculate in the end. And so theta is a parameter. You'll never actually know what it is. It's like mu. You never actually know what it is. Instead, you need to estimate it. And so I'm putting the estimator in there. Any questions about this, at least at this moment? Okay. So, here's a question then for you. Why do you think it's important to know that a maximum likelihood estimator has a particular distribution with a particular mean and particular variance? Why? Where could that be useful? So we can do hypothesis testing. Why else? What's another reason? Confidence intervals too, okay? In other words, inference. We want to be able to do inference because we don't know what theta is. But if we can quantify its estimator, we can get a general idea of what theta should be approximately with a certain level of confidence. That's why we do. That's why this is so important. So let's look at how we can calculate this variance using the actual formula. Again, don't worry about this on the test, but I think it's at least good to see it once. If you take a course like Stat 883, especially for the stat majors here, you'll get to do this a lot. Okay? So, field goal kicking. Here's my log likelihood function once again. We've already seen the first derivative. I can also take my second derivative as well. Notice how I have a negative here and a negative here. I want to find then my estimated variance of pi hat. So, because I could factor out this negative and then basically essentially have a plus in there, right? Notice how I have a negative out there. So what's going to happen? I've essentially accounted for that negative. Or it goes away, I should say. Excuse me. So then what I need to do is I'm going to put in here my the second derivative of my log likelihood function without that negative. I'm going to put inside this expected value. I'll let you go through some of the details on your own, but you'll notice that eventually I get to a point where I have the expected value of a binomial random variable, which is n times pi. Okay? I keep on simplifying and simplifying, and this is what I get. So in other words, this goes right in there. Now, since I want to replace pi with pi hat so I can actually calculate it, so I simply make that little substitution. Also, I have an inverse up here as well. So in other words, I'm going to flip this. And so this is what I get. This is my estimated variance, again, a var with a hat on top of it, of pi hat. To make sure you understand the difference, if I didn't have that pi hat there, this is my variance of pi hat. I don't have the hat on top of it. Yes?
Where's the negative sign?
That's what disappeared. See that right there? If I put this in here, if I put all this right in here, I factor out a negative. The negative times a negative is, so that's where it disappears. I know when I was looking over my lecture notes before class, I was like, oh no, did I make a mistake? And it took me about a minute. It's like, okay, that's what's happened. Okay. So now that I have this, variance, I know what the distribution is for pi hat as well. I can calculate a confidence interval for pi hat. I can do hypothesis tests. I'm sorry, I can calculate a confidence interval for pi, excuse me. I can do a hypothesis test for pi as well. And a very common way to do confidence intervals for any kind of maximum likelihood estimator is to use a method called a Wald confidence interval. And it's based upon this idea. So again, let's say I'm going to be very general. I have just some kind of maximum likelihood estimator. It doesn't have to be pi hat. If I have some kind of maximum likelihood estimator, call it theta hat. Again, it has an approximate normal distribution to it. I can rewrite then this like in this following form as a standardized statistic. You know, in your first stat course, you know, you often did something like this. Say z is equal to x minus mu over sigma, where mu was the mean of x, sigma was the standard deviation of x. I essentially did exactly the same thing there, but now I have theta hats. That is an approximate standard normal distribution to it. So what that means then is that I can quantify probabilities associated with this quantity. In particular, I could take a lower bound from my standard normal distribution, a quantile from my standard normal distribution. I can take an upper bound or upper quantile from my standard normal distribution, put this standardized statistic in the middle, and I know that approximately that probability is 1 minus alpha. To put this into a picture form, let me do some erasing first. What I did was this. I'm going to draw out my standard normal distribution. Of course, it's centered at 0. That is supposed to be a standard normal distribution, trust me. Let's put this into a context of 0.05 for alpha. So then that means then that z, 1 minus alpha divided by 2 would be 0.975, right? All see that? So what would this number be? Z sub 0.975. Get out the standard normal tables in your head. 1.96, yep. If I come over here, I have z 0.025, and that's going to be what? Minus 1.96. And so what I've said then is that the probability that this right here is between negative 1.96 and positive 1.96 is 0.95. Any questions about that? Okay. Now that I got that, I can do some algebra so that I get just theta in the middle, like you would see in a confidence interval formula, right? And then I have on the left side the lower bound, the right side an upper bound. And I still have this probability being approximately 1 minus alpha. So again, if alpha was 0.05, that means 95% probability. Okay. Again, theta hat is a random variable. Once I know what theta hat is, once I actually observe it, obviously it's not a random variable anymore, and then I can use that to calculate an actual confidence interval. So my 1 minus alpha times 100% Wald confidence interval is what's shown there. Please be careful that you understand the difference. I know it looks very the same. In some context, maybe I should have used like an uppercase theta here to represent that this is actually a random variable rather than the lowercase one. But I don't know if that extra level is really helpful. Just, you know, when I'm dealing with probabilities here, I have to deal with a random variable. If theta hat was a constant, I don't have probabilities to deal with anymore. Okay? So once I put in then the observed value of theta hat, I have a confidence interval. And I have a 1 minus alpha times 100% confidence level associated with it, that this is going to work. Okay? Any questions? Well, let's put this back again in the context of what we're interested in, estimating pi. So the Wald confidence interval for estimating pi is, well, pi hat, and notice, I should mention this here, notice how I'm actually subtracting and adding exactly the same thing, so I could instead write this as theta hat plus or minus the z times the square root of the estimated variance. I could write it like that too, and essentially that's what I did right here. There's my Wald confidence interval for pi, which is what we talked about earlier, right? Let me actually go back up there just to prove to you in case you don't remember. Remember when we did this? That's a Wald confidence interval for pi. What did I say about this interval?
Not good.
Not good, yeah. That's a nicer way to say it than bad. And you know, if you really remember using that in another class, you know, some of the details, you know that there are particular rules about when it works. Like if, let's say, n times pi hat greater than or equal to 5, you can use it. Interestingly, in the statistical literature, you know, this is like a research topic that never dies, because people know that statisticians know that people like to use this, but we also know that it's bad, and so we keep on proposing other intervals that are better, but there's never one interval that's the best. And so in the statistical literature, people have talked about this, and they talked about that rule that n times pi hat, if that's greater than or equal to 5, you can use this interval. It's going to work out. Surprisingly, no one has been able to figure out where did that rule come from. And in fact, it's not really a good rule to have in the first place. But yet, in every introductory stat book out there, pretty much, you're going to see that rule stated. So,
Why is it bad? Why is it so bad?
I guess I can briefly talk about it right now, but you will see the details coming up. So when I say 95% confidence, what does that actually mean? Does someone want to volunteer a question? Or question and answer? Roughly speaking, it means this. If I were to go out and calculate go out and take a sample, calculate a confidence, then suppose I repeat that process again and again and again. You know, you're not going to have the same confidence intervals every single time. Let's say I do this 100 times. Each of them are 95% confidence intervals. Then 95 out of 100 should contain your parameter, right? That's what this confidence level actually means. It doesn't mean that one particular interval has a 95% probability. It just means in the long run, this is how it's going to work out. What I mean by bad is, instead of 95%, even though you state it's a 95% Wald confidence interval, instead it might actually be 90, 85, 70, 50. Seriously. I will show you examples. That's why it's bad. So the stated confidence level is not what we call the true confidence level. And we're going to spend a considerable amount of time understanding that in more detail. Okay? Hopefully that will help you see where we're going with this. In addition to that being a reason why it's bad, here are some other problems with it too. Number one, the calculated limits may be less than 0 or greater than 1. So let's say that pi hat was 0.01. Let's say you're doing 95% interval, so that this would be 1.96. You could have a lower limit less than 0. Can you ever have a probability less than 0? No. Okay, that's a problem. Similarly, you could also have an upper limit greater than 1. Let's see. What if you observe pi hat equal to 0? So no successes. Look what happens to the variance part. Your variance is 0. 0, square root of 0 is 0. Then 0 times that 1.96 is 0. So your confidence interval is 0 to 0. That's not very good. But you're 95% confident that it works. So that's another reason why it's bad. Despite it being bad, let's talk about, first of all, let's look at how we can calculate it, okay? And then we'll get into better intervals right after it. So field goal kicking again. Let's say you have 4 successes out of 10 trials. So if you were to do it by hand, which we rarely would do, but it's still good to see how it's done. Simply pi hat is 4 divided by 10. Okay? You put in that 4 divided by 10 there and also there. If it's a 95% interval, you get to 1.96. You do all the calculations, you get 0.0964 to 0.7036. That is your interval. That's one way to state it. I'm okay with stating it this way too, if you want to. Long as it's clear that we're doing an interval for pi. Okay? So either way, it's fine with me. How would we do this in R? So it's a nice, simple calculation here that will help you learn better how to use R. Okay. So here's my corresponding program, cipi.r, that you can download from my website. I'm going to create an object called W that's going to be equal to 4. Do the same thing, similar thing for n. It's going to be 10, alpha, and then I'm going to find pi hat, as you might expect. So if I run that, if I type pi hat, of course we get 0.4 back. So first, or next then, let's actually calculate that estimated variance. So I decided to create an object called var.wall. Naming is obvious why I chose that. And I just simply say pi.hat times 1 minus pi hat divided by n. Put that into var.wall. Then for my lower limit, I create an object called lower. Lower gets pi.hat minus. To do a quantile from a standard normal distribution, you can use the Q norm function, Q for quantile, where the first argument is called P for probability. So the area to the left of it is 0.975. That's why I have 1 minus alpha divided by 2 there. And I take it times the square root, excuse me, var.wall. Do a similar thing for upper, but now I have a plus there. So let me go ahead and do this. So here's my lower, here's my upper, and then I can put this nicely together in a data frame. There we go. Okay. If you notice in my code, I actually use the round function with it just so that it looks even prettier. It's all in the presentation. So that's how you do the calculation. Since sometimes this can be confusing for students, I want to bring this up. So this is square root, SQRT gives me my square root, of var.wall. In other words, I am doing this. Okay. What's another name for this, doing a square root of the estimated variance? So yes. So you could call this your standard error. Hopefully that name sounds familiar. What's another way that you could verbalize this? It's my standard deviation of my statistic. Standard deviation of pi hat. So the square root of an estimated variance of a statistic is the same as a standard error and is the same as the standard deviation, the estimated standard deviation of a statistic. Just want to make sure that's clear because, two words or two phrases, I guess, that mean exactly the same thing. So how would I interpret this then? Here are two. The first one's what you typically learn in like a Stat 218 introductory stat course. With 95% confidence, the true probability of success is 0.0964. It should be the word 2.
Between?
Oh, I guess I did have the word between there. I just didn't, I don't know if I said it out loud. I guess I have to check the video. It is between 0.0964 and 0.7036. Okay? That, if you want to use that kind of interpretation, whenever I ask you to interpret an interval, that is fine. It's helpful, to put it in the context of the problem. We're talking about probability of success for a field goal. So maybe I even should put field goal there too. In a course like Stat 883, Kellenberger inference, you would learn something like this. The 95% confidence interval is 0.0964 to 0.7036. We would expect that 95% of all similarly constructed intervals to contain pi. That's fine too. Where does this name come from? For those of you who have not taken Stat 883, it comes from what I was saying earlier about if you were to repeat this process 100 times, you expect 95%. You expect 95 of the 100 intervals to contain pi. That's where that interpretation comes from. Here are incorrect interpretations. The probability that pi is between these two numbers is 95%. That is incorrect. Now, I know for introductory stat students, even I had this issue when I was just learning statistics. If a professor would have told me that, I would say, what? What do you mean? You had that probability statement up already. And I don't think it was maybe until grad school that I fully understood, no, that is actually incorrect. It all comes down to what is a random variable and then its observed value. So since this is an important point, and I know like in a course like Stat 801, you got so many things going on, you just might not totally catch it. I would just want to talk about it briefly. We'll talk about it in the context of a confidence interval for a mean, okay? So here's your old confidence interval for mean. That should look familiar to you. X bar is your sample mean plus or minus the value from the t-distribution times the sample standard deviation S divided by square root of it. Look familiar? Good. Okay. Now, when this is derived, you end up with statements like this. I'm going to use a capital X bar. Oops. Capital S. And then you do the same thing on the right side here, but I'm running out of room, so I'm not going to do it. Okay? That probability, if you have an underlying normal distribution, is 1 minus alpha. The difference between this probability statement and this up here is the size of the letters. Uppercase letters mean random variables. Lowercase letters mean the observed values. So let's say that I observe X bar to be 3. And maybe the standard deviation to be 2. Let's just say I did that. And I put that into that probability statement. Now, what is that probability? Well, you have no random variables anymore. So you can't assess the uncertainty. Either that probability is 1 or it's 0. It's one of the two. So 95% of the time, pi is between 0.0964 and 0.7036. That is incorrect as well, because pi is a fixed number. Either it is or it isn't.
If you change that to pi hat, would that be the correct statement?
No, because pi hat is always there, because you know what pi hat is. Or, I guess if you're thinking in terms of a random variable, no, I don't think still that would be totally correct. Because we're talking about pi. We're coming up with an interval for pi itself. Pi hat, yes, will vary, but I wouldn't necessarily say that 95% of the time pi hat will be observed to be within that interval. So the 95% confidence interval is this right here. We would expect 95% of all pi values to be within these limits. Again, that is incorrect because pi is one fixed number. Okay. So some problems here. Okay, so this Wald interval, as I said, comes from this this maximum likelihood estimator property that you have this normal distribution. And this works out if you have a large sample size, this normal distribution. Do you think n equal 10 is large? Generally speaking, no. Okay, so that can cause some problems because now you might not be put as much faith into that normal distribution actually being good. Also, something else that causes problems is that the binomial distribution itself, obviously, it's for discrete random variables. W is equal to 0, 1, 2, all the way up to 10. So that means that the actual distribution for pi hat, is it normal? No. It's actually a discrete distribution. And we're using a normal distribution to approximate it. That then causes a problem here too. We'll see actually some cool plots of how that discreteness can cause problems. So then in the end, Wald intervals typically, not necessarily in all cases, but definitely in this particular case, Wald intervals tend to be what we call liberal. Meaning that if I state a 95% confidence level, the actual true confidence level is something less than that. Maybe 90%, maybe 80%. That's what I mean by a liberal interval. On the other hand, there are other confidence intervals out there, and we'll see one shortly, or actually next time, that are called conservative. A conservative interval is one that generally has a true confidence level that's above the stated level. So maybe 97.5% or 99%. We're in here until 3:45. I got 2 minutes. So there could be conservative intervals. Now, if you were given the choice between a liberal or conservative interval, which would you maybe prefer? Conservative. Because if you state a certain level of confidence, I would feel better that I at least got 95%, rather than not knowing necessarily how much lower than 95% I am. So typically conservative are better, but there are some drawbacks to having conservative intervals, which we will talk about too. So this then, again, since the Wald interval is not good, this has led to a lot of research. Even in fact, I have kind of put a paper into the literature on this kind of topic too. Not exactly the one that we're looking at, but I have put a paper in a very similar topic. One of the best papers I think on it is this Alan Agresti paper with Cool. Cool is at Harvard Biostat. And this is when Cool was a student. And basically what they tried to do was come up with a better interval that was easy to calculate, that could be taught like in a Stat 218 kind of course. And they did. They came up with a good interval, and it's called the Agresti-Cool interval. They didn't call it that themselves. People since have decided to call it that. It would be a faux pas to develop a new confidence interval or statistic and decide to call it after yourself. Hopefully someone will start calling some stuff the builder interval or the builder statistic in the future. We'll see. And so there's been a number of papers on this subject. We are going to focus on the results from this particular paper. This was a review paper. And they had some really good suggestions. And they looked into, well, why was the performance bad sometimes? Why was it good sometimes? And stuff like that. So we're going to, based upon their recommendations, we're going to look at 3 other intervals next time. Okay? Are there any questions? Okay, and that's it for today.